let's take a look at vertical circles. Okay, this is sort of like yesterday's topic, but it's a little bit more in depth. So it's exactly the same thing, but there's one more force to consider when you're in the vertical direction. Just like when you had vertical motion, you had to consider the acceleration due to gravity. Well, when you have a vertical circle, you have to consider that. You have to consider gravity, right? So gravity matters when we're talking vertical. Okay. Now, this is a little bit weird because it's not really a uniform thing. Think about this right here. If this is a string attached to a rock or an object or something and you're spinning it in a circle this way, right here, as this thing's being pulled up, not only are you supplying a force to make it accelerate towards the center of the circle, but you're also supplying a force to pull against gravity. Okay? So your net force here, if we go through and we try to label all those forces, you've got tension in the string, Ft, and you've got mg, the force due to gravity. So the net force is equal to the tension force minus mg, which is going to cause this thing to actually have some centripetal acceleration, right? It's got to accelerate towards the center, which equals Fc. Okay, and so what we can see here is the tension in the string at the bottom of this curve is equal to the centripetal force plus the force due to gravity plus mg. Okay? Now if we just go a split second later in time and we're up at the top of the circle, there is those two forces acting still, but this time the tension force is down because it's pulling it towards the center of the circle, and gravity is always down. So if we look at the top of the circle, we have net force equals Ft plus mg, and that's causing this thing to actually have some centripetal force or keep moving in the circle. Okay, and so what we see here is the tension is equal to the centripetal force minus mg. Okay, and so just like you'd expect, it takes more force to pull something up than it does to pull something down, because gravity works with you on the way down but against you on the way up. Okay, so these are two equations that are fairly important. Top of a circle, bottom of a circle. Now what if you're looking right here at the side of a circle? Okay, well then you have mg here and you have Ft here. Okay, and these two forces being perpendicular to each other, they don't really add, right? So your tension force is not so bad. Now we're not going to look at that case in depth, but one thing we are going to look at is like a roller coaster loop. Okay, you come into a roller coaster loop, comes up over here, okay, and you come out. So right here at the top of this loop, okay, you don't actually fall out of your seat. Okay, gravity's pulling on you, but you don't fall out of your seat. And the question we have to consider is why? Okay, why don't you fall out of your seat? And it's because there's multiple forces acting on you. Yes, gravity does pull down. However, if that was the only force acting, you would actually fall out of your seat. Okay? But it's because you're moving in a circle, right? Newton's first law says an object continues in a straight line unless a force causes it to change. So you want, after you come up off this circle, you want to keep going in a straight line. But you don't, because the track is here to keep you from that. So the track is actually exerting a force on you in this direction. As long as this force is here, then your acceleration to keep you in a circle is greater than the acceleration due to gravity. Okay, so here's what you have to keep in mind. The centripetal acceleration is greater than g if you don't fall, right? If you do fall, then the centripetal acceleration is less than g. Okay? And so one of the things I like to ask is, what's the minimum speed you can have up here if this circle has a radius r? Okay, what's the minimum speed you can have? Wow, I spelled radius wrong. And still stay in your seat. Okay, and so it goes back to that vertical circle thing where we had the net force is equal to, except this time it's not tension, it's actually a normal force because the track is exerting it. The normal force plus mg, they're in the same direction, equals Fc. But remember, centripetal force is really just mv squared over r. Okay, so what we have here is the normal force. okay, plus mg is the centripetal force. Now essentially what we're saying is that we need to have a normal force, but it could be incredibly small. Okay, so we're just saying the force due to gravity is a little bit less. So what we're saying is mg is less than Fc, which equals mv squared over r. And so what we really have is mg is less than mv squared over r. Okay, and then we can see that the mass cancels out, and g is less than v squared, I don't know why I squared that, over r. And so if I wanted this speed, I would just multiply both sides by r, and I would get v squared square root. Okay, and so this is the minimum speed that you need at the top of the roller coaster in order to actually stay in your chair. And I guess this is less than v. Okay, so v needs to be greater than the square root of rg. And there's going to be a couple problems for you guys to work, but basically when you go into a vertical circle, it's a lot like a horizontal circle. You just have to keep gravity in mind.